address different problem than we did last 2 times. The idea is to consider a domain, again filled with a viscous fluid. However, the domain that has one part of its boundary that is porous, not solid. So we allow lower part of the boundary to leak. This kind of problem is very much in line with applications and has been addressed by many authors so far. Our goal is here is assuming the periodicity of the pores of this porous boundary to try to rigorously derive the effective condition to be imposed on such porous boundary. For the sake of the presentation, we are going, unlike last time, for this problem we are going to to consider a 2-dimensional setting. These results have already been extended to a more realistic 3-dimensional setting. However, the main principles and the main approach remained pretty much the same. So you can put the title, the effective boundary condition on a porous wall. And the results I'm going to present you today and most probably next time are contained in the paper written by Edvard Marušić-Paloka and myself that has been published in Zeitschrift für angewandte Mathematik and Physics last year. So these are rather recent, again rather recent results. So for the generalization on the 3D problem, of course, which carries some technical difficulties, but the main approach is similar. I refer to the paper published this year in International Journal of Engineering Science. Again, we were able to publish our results in this top engineering journal. And as with the Darcy-Weisbach, we expect that this result is going to be recognized in the engineering community. And why is that so? Because essentially what we do, we propose a new boundary condition to be imposed on a porous boundary, which is essentially of the so-called Darcy-Beavers-Joseph type boundary condition, which in case of a 2-dimensional setting essentially splits one component to Beavers-Joseph, famous boundary condition, and the other one on Darcy type boundary condition. Okay, now we will proceed with the description of the geometry. So let us put the subtitle setting of the problem, where we are going to precisely describe the geometry of our domain and as well the equations, the starting equations. Okay, so let A be in this range, and let us define a set denoted by capital A. It is obvious that the closure of this set is contained in this interval, and this we denote by y. We also introduce B as this complement, which is essentially this one here, if we take into account the... Okay, and now we define the porous part of our boundary. For the sake of simplicity, we assume that the lower part of the boundary is the one that is leaking, that is porous. So we introduce gamma n as the following set. And gamma d as the following set. So the description of the porous boundary is rather classical. There is nothing new there. Maybe you have not seen it so far, but and now, as I said, for the sake of the presentation, here we consider a two-dimensional domain. In fact, more precisely, we consider a simple rectangle that has porous lower boundary. And for L greater than 0, and introducing small parameter, of course, in the problem, denoting the size of the pore. We define the following. So we defined already the omega. We define the upper boundary by denoting it with sigma. The lateral boundary is denoted by gamma. The following set is also introduced, T epsilon. And now we define first gamma epsilon k d as this one. So we are assuming the periodicity of our pores, and analogously gamma epsilon k n and now we put the union of these sets as this set here. and this set here. So essentially, what do we have? We have a rectangle domain, omega, where this upper boundary is sigma. So this is our omega. And with lower boundary that is porous. So this lower boundary is denoted by gamma, and we have two parts of it. This is the wall part, denoted by superscript d, and this is the whole part. These are holes which are periodically distributed, which is denoted by superscript n. And this should be remembered throughout the lecture. So this is the description of our domain. The equations are simple, so simple Stokes. So here we do not want to address inertia effects because the analysis by itself is rather complicated due to this complicated domain. So domain is two-dimensional, but we have here a porous boundary. Okay, so the equations are the following. Simple Stokes system, so linear Stokes system. We assume the inflow condition here. So we assume that on sigma we have the prescribed velocity. And now the question is from which boundary condition to start on this lower part gamma. So essentially what we do is on each hole we impose the value of the exterior stress. It is natural to expect that this value will correspond to the exterior condition. In our case, the exterior pressure. So on each hole, and hole is denoted by the superscript n, we assume, and this is the corresponding part of the boundary that collects all holes on the lower part of the boundary, okay? So on each hole we prescribe the value of the normal stress. That means that we put the stress tensor of the which is naturally defined as the following. So this is classical stress tensor. So on each hole, and this is the part of the lower boundary that collects all the holes. We prescribe the value of the normal stress, which we will denote by some function h having two components P0, Q0 and P0. Now what remains to close the problem? It remains to impose boundary condition on the wall part of the porous boundary and of course on the lateral boundary. So for the wall part of the porous boundary, we impose classical no-slip boundary condition. And now the question is what to impose on the lateral part. Similar question we had in the case of Darcy-Weisbach. Since here I want also to present you, that will be done next time, the result of rigorous justification, we put here the periodic boundary condition on the lateral boundary. So we assume that both velocity and pressure, which are unknown in the governing system, are periodic with respect to the first variable. And this is our starting system, which we denote by 1, labeled by 1. In the following, of course, all functions are, so these functions are given, they are also periodics with respect to the first variable. Of course, this is the viscosity of the fluid. So this is our starting system. This is our small parameter. And now the idea is to start to derive the lower dimensional application. And as a part of this approximation, to obtain the effective boundary condition on a porous part of the boundary. The approach relies on homogenization and boundary layer theory. There are some similarities with a work on Darcy-Weisbach, but the problem is quite different because first we do not here address the inertia term, so the problem is linear. However, this boundary condition is, this dynamic boundary condition is very complicated. Okay, so now we proceed to analysis. I will keep this domain just to have in mind. So we have a wall, which is by D, and we have holes, which is denoted by superscript n. That seems to be important in the following. Okay, so the subtitle could be Asymptotic Expansion. So the idea is to expand the unknown functions in the powers of small parameter epsilon. In other words, to approximate the solution that we do not know exactly with the following approximation. Note here that this x is essentially, and that the fast variable will be denoted by epsilon, which is this one, okay? Similarly for the pressure, however, for the pressure we have to start by 1 over epsilon. So we have something like this. Of course, we assume that all functions are periodic with respect, with this period in x1 and the first component of the fast variable. So this is the idea, to try to determine these guys here, of course by plugging this into the equation. You notice the difference. So we do not have here a thin domain. This is not a thin domain case, okay? This is the case where we have periodically distributed holes where epsilon is the size of the pole. So the expansion is the following. Now plugging this expansion, which we can label by 2, leads to the following equation, of course, by identifying the terms with equal power of epsilon. So as you can see, the lowest the order will be epsilon to the -2, yeah, due to the fast variable and the second order nature of the Stokes system. So by this exponent we have the following. So for the zero order approximation, we have this Stokes system with respect to the fast variable. The next term gives the following. Notice that now we have to take also into account the derivatives with respect to the variable x. So these are mixed derivatives, yeah? And for the U1, we have this. Okay? So this is the problem for this pair of functions. And finally, we will need also this another term, which will lead us to effective equations. So from these two problems, we will essentially derive the effective boundary condition, which is going to be in the form of the Darcy type boundary condition. For the two-dimensional domain, it will split into the two parts. But to derive the effective equation, we need also the problem for U2. And from the divergence equation, we obtain the following for U2. Yeah, I got it text, yes. Thank you. Okay, these are the expressions that we obtain by plugging this to a Stokes equation. Now we have to focus on the dynamic boundary condition and see how first this symmetric part of the gradient can be approximated, leading to the approximation of this. So we will consider this together with dynamic boundary condition and the boundary condition on the rest of the boundary. So this deformation tensor can be approximating as following. Okay, now I have to erase something. I will erase this. Excuse me, capital. So we are seeking for the approximation. So we are putting this into the symmetric part of the gradient. You know how this is defined. And when we take this into account, it leads to following. So this is simply by the definition applied to our approximation denoted by capital U epsilon. Okay, and now we have to consider the expansion. It's a very complicated expression, but I will write it here. Of course, we are again collecting the terms with equal powers of epsilon. So we have the following. Excuse me. So this is due to this term here, yeah? This says x1 over epsilon, so we have this. We have this. This. And we have this. I will write one more term. So by 1 we have the following. So the same here. And here we have this. And then we also have the term by epsilon and also have the term by epsilon squared. But for now, it is enough to write this. Okay, so this is nothing much clever. We just use the definition for the symmetric part of the gradient and apply it to our approximation denoted by capital U epsilon. And now taking into account the dynamic condition, which is, if you recall, stress tensor, the normal component of the stress tensor equal to the exterior pressure. And taking into account this, we derive the expression for the dynamic condition, which I will write here. So you can write 1, 3. I think that this is 1, 3 leads to the following. There are problems with this. This is capital Q0. This is capital P0. So let us denote all this by 3 and this by 4. So this is described on gamma, the epsilon, n, so on holes, yeah? And on the wall part of the porous boundary, we have a simple no-slip boundary condition. Before proceeding, I would like to stress how we obtain this. So we have the stress tensor. Excuse me, this is not a vector. So this is the stress tensor applied to our approximation, okay? Capital U epsilon, P epsilon. So we have this, yeah? And now we just used the starting boundary conditions, which says that we impose the normal stress, okay? So take this into account, obtain this one, by taking into account the first two terms. Okay. And now let us construct U0 Q to the -1, so zero order approximation. by taking into account this. The no-slip boundary condition, and the equation, and the expression for the dynamic boundary condition. Okay, now I will erase this. Now this is also the important. So first, the answers for U0 q to the minus 1. Okay. So the idea is to seek for the solution in the form, of course, as for the Darcy-Weisbach, here also we will have to introduce the suitable auxiliary problems. But there is one trick in posing those problems. So we are looking for the solution in the following form. So we separate the variables, the fast one from the other one. Both for the velocity and pressure. So these are scalar functions that are unknown. And that will essentially be our effective velocity. Okay? And now when we assume that the solution of this problem has such kind of representation, we deduce the auxiliary problems to be imposed and satisfied by this function. Of course, where this auxiliary problem is posed, it is imposed in an infinite strip. Because this other variable is fast. So essentially, we have this. This is our G, where the whole part is denoted by N, and the whole part is denoted by D. Now there is no doubt what to impose on the whole part. However, in imposing the dynamic boundary condition, so taking into account this, we make a certain trick. And the trick is to impose the following. So the stress tensor applied to auxiliary functions in the normal direction we put to be equal to this. So here we do not assume some summation argument, so this is not a summation, okay? This is not the convection, that's the situation where we have two indices that are repeating, and then we assume that here is some kind of sum. No, so no summation with respect to the index k. Okay, I will comment on this constant. We have to close up the problem. So on the lateral boundary there is no doubt. We have to keep functions periodic with respect to the first variable. As seen before, we also need to demand this. And now one more condition, which makes this problem essentially overdetermined. But however, we have the liberty to choose this one. The liberty to choose this one in a way that the auxiliary function in the infinity stabilizes towards the canonic vector. So due to this problem is overposed, you know. However, this is not given in advance. So it's a part of the problem. So we have the liberty to choose this one. Of course, we need theoretical results that are developed in this paper, in the appendix of this paper. So we have the liberty to choose this one in order to satisfy this, okay? So maybe you should write this problem. So the problem, let us denote it by 5. The problem 5 seems to be overposed. Since the behavior at the infinity, 5, 5, cannot be prescribed. Cannot be prescribed. However, constants tau k, from 5, 2 are not given in the advance, In other words, they are the part of the problem. Okay. What to erase now? I can erase this one.